I'm Michael Pardo. I work at Instacart on the platform team. But in 2010, I got my first full-time Android job. I joined a small startup called Mobiata, and we made premium travel apps. And we were doing pretty well with #1 spots in the app stores. And so Expedia took notice of what we were doing at Mobiata. And in late 2010, they acquired us, and we became their mobile arm. So in 2011, the following year, we began work on the mobile bookings app for Expedia. And I had an experience writing that app that I would continue to see, for the next 8 years, all the way up until now. And it revolves around this feature. So we call this the hang tag loading indicator. And this was in the height of skeuomorphic design. So this is like a hang tag resting on a doorknob. And we wanted to delight and entertain the user while they were waiting for search results to come back. This is when networks were really slow, and in a big city, it might take a long time for your search results to come back. So I did the Android implementation. There was an existing iOS implementation, it was half done. And although we were writing the same feature, there were small differences that may not have a big impact overall, but they were different enough that it mattered to us. So on the iOS implementation, if you let me explain the hang tag first. So if you were waiting for your search results to load, you could interact with the hang tag and spin it around, and it would spin around the doorknob. You could use the accelerometer to play with it too. And if you spun it enough times on the iOS app and reached a threshold, this little indicator would pop up to show you how many times the hang tag had spun around the doorknob. Now, I missed that feature. It wasn't documented anywhere. But on Android, I had a different implementation of the physics. We used the same angular momentum and gravity from the accelerometer, as input into the physics simulation. But one thing, I took one step further than iOS, and since this is skeuomorphic design, when you lay the phone on the table, it should interact with the surface that it's laying on. And so friction was something that I took into account on Android. And so if you laid the phone down or the device down on the table in Android, the hang tag would slowly come to a stop, taking into account that friction. But on iOS, it would just keep spinning and spinning and spinning. So this is the first time I encountered some sort of scenario like this where we had the same features and slightly different implementations. And I continued to experience this across teams, across apps and companies. And I think this, for many people, this is what mobile app development looks like. And we both have our respective teams. We start off with good intentions, with feature parity, everything is going great. And then maybe one of the teams will get their designs first. And so they're the first to release the next feature. And then not long after that, Android or the other team will get their final designs, and so then they can release. And it took some time, but once again, we're at feature parity. So the next release goes better than the last. We were able to maintain feature parity, but one of the platforms has introduced a regression in this bookmark feature. And so they create a patch release and fix the bug, and now they're 1 point released higher. Once again, this happens, but in reverse. We released with feature parity, but we have a regression on this feature on the other team. And so again, we follow up with a patch release, and we leapfrog in versions again, another point release. And so this happens indefinitely. Does this feel familiar to you guys? Yeah? So this is the state of many of things for many of us. We work in this environment of inconsistency, and it shows in our products. The size of our teams are inconsistent. The tools that we use are inconsistent. They're different, and we have fewer or more depending on the platform. The quality and the comprehensiveness of the designs that we receive are inconsistent, and we will likely receive them at different times. And our schedules and our deadlines for each team are inconsistent. So what is the real problem here? And I think at the core of this inconsistency is the fact that we're solving the same problems, but in different code bases. So how do we fix this? And this is my vision. Instead of many different code bases per platform, we have one code base, one team working together to solve problems once in this one code base. So we have a single core team with platform specialists adapting the application core to run in their respective platforms. This concept is not new, and in fact there are many options that exist to tackle this problem. So here are a few. Let's go over them. First up is Flutter, and this is one of the latest attempts to solve this problem. So Flutter is a mobile framework that is written in Dart and then ships with a Dart runtime to all the supported platforms. And it ships bundled with an entire UI framework. And this framework renders the UIs similar in a way to how like a video game would render a menu screen. The UI is declarative like React, and it adapts to each platform to respect the feel of the platform. So how each platform lists, the list scroll, how navigation works. But since the UI components are not native, it's up to the Flutter team or the Flutter community to maintain this consistency over time. React Native uses native components instead to render their UIs. And so they have abstractions over the UIs and the components, and they have to be translated to their platform native counterparts. But once again, you're still constrained to the least common denominator of UI elements and of platform features too. So once again, your tool set is fairly constrained to the speed at which React Native, the React Native team, or the community is working. Another framework, Ionic, they tackle this problem somewhere in between the two, where if you want to use native UI components, they use Cordova or PhoneGap, or you can export the application as a progressive web app. So these are all more multi-platform frameworks, and what they do is they try to solve the problem using abstractions of both logic and UI. And I think that extending abstractions to the UI rendering might be a step too far. So you're constrained by the framework's features rather than the platform features. You're constrained by the pace at which the platform is iterating, and you're constrained by the community and the ecosystem of the framework. And I see frameworks as essentially architectures with implementations of their abstractions. And you're handing a lot of control over to the framework, which means you lose out on a lot of flexibility. And I think the correct way to address this problem is to remove the implementations part and just focus on the abstractions. So specifically, the way I like to solve this problem is by using multi-platform functional architecture. So let's break this down into the individual components. Starting first with Multiplatform, and the tool I use to accomplish this is Kotlin Multiplatform. Without going over too much of the mechanics of interop and expect actual APIs, Kotlin Multiplatform works like this. So at the inception of Kotlin, it was a JVM language. It compiles to JVM bytecode and runs in a Java virtual machine. Later, support was added for JavaScript, and this works just by transpiling Kotlin source code into JavaScript sources. And then later, native support was added. This is done by writing a LLVM backend for the Kotlin compiler. And then most recently, all these tools were consolidated into one single tool called Kotlin Multiplatform. All your target agnostic code is written in this common set of sources at the top. And then it's built for each target that you specify using the tool. It's still a work in progress and has a lot of caveats, but I think the work being done here is very promising, and in the end it's an effort worth getting behind. So that's the gist of Kotlin Multiplatform, and while not yet perfect, it's the tool that I'm using to solve this write once and deploy anywhere aspect of this concept, this overall concept. Next, to understand the functional architecture aspect, we have to first look at the functional part. And so when I say functional, I mean functional programming. This talk isn't about functional programming, and we're not going to talk about category theory or monads. But after spending many years studying functional programming and architecture, I think understanding the basics will help. So functional programming is essentially an implementation of the lambda calculus. And lambda calculus is a simple notation for expressing what is the core of computing. This is the simplest lambda calculus expression that you could write. It's an identity function. So whatever you give it, it just gives back to you. And there are three mechanisms that make up the lambda calculus. So we have abstractions, and to us these are just functions. We have variables, and these are the parameters that you pass into the functions. And in lambda calculus, these are bound by applications. The function body is where we use these variables. And third, lambda calculus defines application. So this is just the expression that we are binding to the other expression's variable. So application is done just by simply replacing the variables in the abstraction. So this variable x was bound or replaced by the expression a. And then you replace all the same terms in the body. Once you do that, you can drop the head off of the abstraction, and you're left with the final result of the evaluation. And this process is called beta reduction. And that's all there is to lambda calculus. But from these simple concepts, you can represent anything that you can represent with a Turing machine. For example, this is FizzBuzz written in lambda calculus. Now, we wouldn't actually want to write this, but the point I'm trying to get across is that we can, and the power behind these simple abstractions, these simple concepts. One notable quality about lambda calculus is that expressions are pure. And this is why functional programmers like pure functions. So there are two qualities that make it pure. The first is determinism. And what this means is just that for any input of a function, the output will always be the same. And so to demonstrate, let's look at an example. So here we have a function. It takes a list, and it returns the first element in the list. Does this function work? Yes. Given a list, it will return the first element. But is it deterministic? No. So this line does return the first element by popping it off the list. But it also mutates the list And so each successive call to this first function with the list is going to produce a different result. This implementation is deterministic, though. For the same input, it will always return the same output. It doesn't mutate the list that was passed in. And this quality of determinism enforces consistency in your code, which is what we want. Another quality of pure functions is that they don't perform any side effects. And a side effect is unseen behavior of a function. There is an unintended consequence of calling a function that has side effects, and it's not known to us, it's hidden from us. So using this same deterministic function from before, we can see that it's still not pure, although it's deterministic, because the function prints to the console. And from the outside, there's no way to observe that it's doing this. We don't know about it, it's hidden from us. And so just by removing that side effect, this function is now pure. We'll know that it always does the same thing. It does nothing more than it advertises. And so these two qualities make us feel very confident in using the function. So these two confidence-building qualities can derive another quality of pure functions called referential transparency. And all that means is that if a function is pure, we can be confident that that this expression right here is equivalent to this one. There is no difference. And given a composition of pure functions like this, we can take out all of the middle, and it'll look something like this. And this looks like beta reduction, right? So abstraction and composition are at the core of computing. And using just these concepts, nothing else, we can express anything. Anything except side effects, which is something that we need. You know, a program would be useless if we didn't have side effects, if we couldn't store to the disk, if we couldn't get network requests or log to the console or render to a screen. So the question then becomes, how do we mix this world of purity and impurity? And that's where functional architecture comes in. So to me, functional architecture is all about boundaries. So at the core of our architecture, we have this island of pure code, and at the edge of the code, we have this heavily guarded border. We don't want anything impure coming in. But we need to interact with pure code, right, in order to produce these side effects that are useful in an application. So what we do is provide some way to get into this pure code and interact with it. We create these ports. And now we have this well-defined way to dip into the pure world from the impure world. And then we adapt our impure code to fit into these entry points. And we can plug them in. So just like functional programming, functional architecture is also about abstraction and composition. These same concepts from lambda calculus. In other words, functional architecture is ports and adapters architecture. And there's other names for this: hexagonal architecture, onion architecture. I think most of us are most familiar with clean architecture. But if you take those and strip away all the ceremony and all the prescription applied to those, you're left with this simple idea of ports and adapters, or abstraction and composition. So functional architecture is the style. But if we want to see the architectural style in practice, we need to look at some of the patterns. And architecture patterns are just taking a style and applying it to a context. And I think the context that I want to look at, and the one we're probably all most familiar with, is application state. And the most common application of functional architectural style to application state is unidirectional architecture. So these are some of the most popular unidirectional UI architectures from the web. We've got Cycle.js, which is MVI, Redux, and Elm architecture. Elm architecture is MVU. They're all very similar, but they differ enough that you will most likely want to pick one over the other. One thing that all of these libraries do, though, is they provide you a way to quarantine your effects and make them safe. At a high level, though, they all work the same way. So there is an initial application state, and that's given to the runtime. The initial state is given to a function which returns the representation of the UI. The runtime then renders that UI representation, and it has some way of generating events. And those events are then interpreted by the reduce function that you supply and turned into the next state. And the events can also, the reducer can dispatch more events to be interpreted later after some effectful thing happens asynchronously. And so this just happens in a continuous loop, and that's why it's called unidirectional. It just flows one way. Another way to think about this is a fold. So a fold function takes an initial state, and this list of events is what drives the iteration of this fold. And for each iteration, the fold function is given the previous state and the next event. And it's this function's job to interpret the new event in the old state and then return a new state. So let's look at some of these patterns in detail and see which one fits the architectural style, the functional architectural style best. First, model view intent. So one thing about MVI architectures is that it relies very heavily on reactive streams. So like RxJava streams. They are at the core of the architecture. They are what drives it forward. UI events come into your main function using observables. From those observables, you then determine the intent of those events. And from that intent, you can create a new model to return to the runtime. And so what you give the runtime is a stream of UI trees that are created from this transformation. So in MVI, or at least in Cycle, effects are managed by functions called drivers, which you pass off to the runtime. You don't see them here because they're not handled here. And there's also kind of nothing preventing side effects from running in here. Redux. Now this looks more like a fold function. So Redux reducers, they take the previous state and an action, and then they combine the two inputs to return the next state. Side effects are handled by giving the runtime a function again. These are called middleware, and you can have many of them. And what the middleware does is they intercept the actions before they get to your reduce function, and they run the side effect and then return another action as a response. So this is similar to MVI in that it requires discipline in the reducer to keep it all pure. Also, effects are not built into the library. It's something that you have to add, and it's part of the ecosystem. Also, instead of returning UI trees, all that Redux does is manage the state of the application. So in order to render it, you need to subscribe to the state changes and then do your rendering. Model view update. This is a general term for the Elm architecture. And this is actually listed as prior art by Redux. Redux got its inspiration, or at least in part, from this. So Elm is a pure functional language, and it comes bundled with this architectural style. It applies it to its runtime. Again, this looks like a fold, but rather than accepting any type, like in Redux, you have to provide a type of message that it knows. It's a typed reducer. So this means that messages can be exhaustive, and that any mutation to the state is going to be known at runtime. You know everything that's going to happen to your application state. In fact, you can pre-compute it if you really wanted to. Effects are also managed by this update function. So you're not just returning a new state, you're returning a new state paired with a managed effect, a description of the effect that you want to run, and it will be run in a deferred manner later. So I've written Kotlin code in each of these styles. I've even published libraries in each of these styles, and also like in this order too. I visited Cycle first, then Redux, and now I'm on to MVU. But to me, I think MVU is the best application of this functional architectural style to state management. And so that's why I wrote Oolong. And Oolong is a model view update implementation, and it's written in Kotlin multi-platform. So let's take a look at the counter example again in every detail in Oolong. So as usual, the unidirectional loop starts off with an initial state. We have a model class with a counter count inside of it. And what we return from this state is from this initialization function is this empty state, and then a none, which is just a function, a utility function to represent no effects. So all the messages are known at runtime and are exhaustive because they belong to a sealed class. And you can compose these too. The update function takes the message and the previous model. So in this instance, if the message is increment, then we copy the previous model and mutate the count, adding one. And if it's a decrement message, then we do that, subtracting one from the count. And once again, we return this model with no effects. We have a props class, which is like a representation of the UI. It tells the render function all the UI elements that need to be rendered, and also the messages that we want to be able to send. The view function, so the view function takes the latest model and then transform that into a props instance, which gets passed on to the runtime. And so to hook all these up, we create a new instance of the runtime, passing in the functions that we just defined, and then one more function called render. So this is all our pure functional code. And this is our platform shell, the adapter that wraps around the functional core. Now, as a bonus, we can extend this desire for purity in our code to the UI rendering, and this is where declarative UIs come in. The front-end web development community has been doing this for years with projects like React, and we're just starting to catch up in the mobile app world with libraries like Jetpack Compose, Swift UI, and Litho. So while the former two are still in development, not quite ready, Litho is, and so that's what I like to use at the moment. It's written by Facebook, the people who made React. But let's imagine writing this counter UI with Compose and see what it would look like. So using Compose, we define our render function as a pure function, and we let the library, the Compose library, handle all the impure code of diffing and patching and mutating view trees and handling click events and all that. And so what we pass to this pure function then is the model and a dispatch function, which is provided by the runtime. So using the model, we create a text element with the model's count and an increment button, which when clicked will pass an increment message to the dispatch function, which was defined in the model or in the props. And a decrement button, which when clicked will pass the decrement message to the dispatch function. All right, let's see the code. So to explore these concepts further, I wrote an app demonstrating all of them. And this is just a dice rolling app. This is written with Litho and Oolong. And so there's an Android implementation and then a SwiftUI iOS implementation that's not quite as good. So it just creates these side effects of random numbers between 1 and 6. Those are impure effects. It'll demonstrate dependency injection. So you see there's a history of the dice rolls appearing at the bottom, and that's persistent across application instances. So there's an implementation in iOS and in Android. And then also we're using declarative UIs using Litho and SwiftUI. And all this is using Kotlin Multiplatform and Oolong. And to show you something in action, if I can, since I have time, there's quite a few samples up on the Oolong website. This is, if you spend any time in the web development world, this probably looks familiar. This is 2D MVC as implemented in Oolong. So this is all using MVU architecture. Right. These are done. So, what I want to say in summary is, I want to leave you with a few, core concepts to take away from this. Purity is one. Boundaries. This is what I think enables the mixing of pure and impure code in this functional architectural style. And then abstraction and composition. So, if you have questions, I'd love to take them. There's a slide deck up, a Slido thing up there. If you want to check out Oolong, it's at that URL. And also, if you want to check out the Dice app, it's on my GitHub over here. So. All right, so if you have questions, I'll take them on here, or you can submit them up there.